Okay. Hi, everybody. We are going to have our next seminar for XFC 2024. We've already had a couple on fuzzy systems and gradient-free optimization, along with an introduction to the game Kessler. Today, we're going to be talking about explainable AI and potentially some topics related to that and fuzzy as well. Our speaker today is Dr. Scott Dick from the University of Alberta. Dr. Scott Dick received his bachelor's, master's, and PhD from the University of South Florida. He is now a professor in the Department of Electrical and Computer Engineering at the University of Alberta. His research interests are in the areas of computational intelligence, including things like fuzzy logic and neural networks, machine learning, data mining, as well as the application of those. And his more recent interests are in multi-valued logics, especially in complex fuzzy logic, along with deep learning approaches, as well as XAI. He's also heavily involved in NAFIPS, the North American Fuzzy Information Processing Society, where he helps organize and publishes many papers on those topics as well. So without further ado, I'll turn it over to Dr. Scott Dick to talk about explainable AI.
All right, thanks, Tim. Well, hello to everybody who may be listening. I see one live guest. Hello, Samuel. So I'm going to go ahead and start sharing my screen. Okay, and we're going to pull up. Okay, so we'll initiate the presentation. There we go. So, whether it's morning, afternoon, or evening, hello to you all. As Tim said, my name is Scott Dick, and for my sins, I am currently a professor of computer engineering at the University of Alberta. Today, I'd like to talk about explainable AI, or XAI, and how it relates to fuzzy logic, historically, currently, and what the future may look like. Some acknowledgements first. My thanks to Tim Arnett and the rest of the XFC 2024 organizing team. Thank you for inviting me to give this talk, and I hope everybody's going to find this a useful resource for the competition. To all my friends and colleagues, thank you very much. This has been a warm and welcoming community ever since I joined the community as a wet behind the ears PhD student, showing up at Fuzz IEEE in San Antonio in 2000. Thanks for all the conversations, advice, and questions since then. And of course, to my students for teaching me so much. In particular, this presentation is based on work with my PhD student, Motaba Yaganaju, which is not just to appear, but actually has been published now in Plamen Angelov's Handbook on Computer Learning and Intelligence. So, why are we here? Well, the economics of AI is what's really driving all of this. There's an estimate out there that about 50% of all job tasks in the North American economy could be automated. Now, that doesn't mean eliminating half the jobs, actually, just optimization. Only about 5% of jobs are seen as actually vulnerable to being completely obsolete. But AI is thought to be able to take over some of the more mundane tasks, and improved automation gives us better productivity growth. Specifically, people think it will help push North American productivity growth back above 2% per year, which is kind of the benchmark that North America was managing for a lot of years, but it's dropped off in the last decade or so. If that happens, it'll add about $3.5 to $5.8 trillion per year to the economy. And anytime you can actually start quoting trillions around a technology, that's an important technology. That's just North America. Something that's similar is probably in the pipeline for Europe as well. So it's a very important thing. But why should we trust an AI? Modern deep networks are black boxes, and their decision-making process is opaque to us, sometimes even being incomprehensible, even to a human expert in the area. So a good example happened in the very famous game between AlphaGo and a human champion, Lee Sedol. Along at the 19th move in the second game of the match, the computer made a move that some of the commentators, who were themselves Go experts, thought was really funny. They were saying, I've never seen a high-level human champion actually play a move like that. They called it creative. Okay, we don't really know what's happening inside the guts of a deep neural network. And yes, sometimes it leads to good and unexpected results, but unexpected results can also be bad. How do we know that the next action of the AI will not have it wandering into an area of the problem state space that has not been well trained, that does not have lots of examples? It also raises the emotional question of fear of the unknown. We are dealing here with an interface with humans, and it's important to acknowledge that both of these viewpoints are actually valid and important. Both of them are critical to the future of AI. Even if one of them is irrational, that doesn't matter. People are not fundamentally machines. We are not fundamentally rational, no matter what the economists will tell us. So we need to deal with the technical and the emotional response of humans to an AI. And if that response is not trusting the AI, humans might just walk away from it. After all, humans have walked away from the AI revolution before. There's no reason they can't do it again. So what to do about it? Well, in 2019, the European Commission had a high-level expert group that came up with principles for what trustworthy AI should be. So it should respect human autonomy. It should not do us harm. It should prevent harm. It should be fair. And the fourth one is explicability. In other words, it has to be able to explain itself. This is rooted in the right of an EU citizen to contest a decision or action that impacts them from a private or a public entity. Could be an administrative complaint, could be a lawsuit, etc. But the ability to contest something is fundamental to the Western concept of freedom. In order to give effect to that right, the human must be able to receive an explanation from any decision-making thing, be it a human or an algorithm. And they have to be able to understand that explanation and take action about it. In other words, we have to be able to explain the reasoning behind an AI's decision in a form that a human can understand. This is also contained in the EU's Data Protection Directive as the right to an explanation, which also requires that citizens be able to receive an explanation for any algorithmic decision that affects them. So explanation is actually a right, formalized in European Union law. And since the European Union is 450 million people, that is a very influential thing that affects AI all over the world. Something similar to that is probably going to wind up being put into law in the US, probably in a weaker version, but it'll still be there. But you know, explanation is not just a right. It's also a strategy for building trust in AIs. There's a number of studies going back decades that say that if an AI can explain its decisions to a human, humans are more likely to trust it. Okay, let's try and break that word down. Trust. What is trust? It's a very big question. Trust touches on almost every aspect of the human experience. And every field that touches on humans has its own definition of trust. It's a giant tangle, let me tell you. I've done some research in the area, and every definition I've seen of trust does actually come back to the question of, are you letting yourself be vulnerable in some way? It's a choice we make to be vulnerable to another. It might be based on reasoning about the legal constraints or the cost benefits of the trust relationship to the other person. It might be based on an emotional connection to another person. But whatever the foundation of that concept of trust, there's always the element of risk, because the other person is themselves a free, autonomous being. They could decide to betray us. So you have to actually extend the trust and make yourself vulnerable to somebody. And now we see why explanations are so vital in AI. How do we make a deep neural network trustworthy? Well, there's no emotional connection. There's no legal constraints or cost benefit reasoning. The AI is not a person. It does not have goals and values and desires that we can evaluate. It is a mathematical function, a fiendishly complicated one, but just a function. It does one task very well. That's what it is. If there's nobody there, we cannot actually apply most of the strategies for evaluating trust that we have evolved in the some millions of years that humans have been around. Trust in an AI means that users have to assess the fit of that complex mathematical function to their own needs. You have to do it within the limits of human cognition, and you have to do it with no specialist training in AI. That's what it takes. And are we vulnerable to AIs? Oh, yes, most certainly. We have already been burned. Prison sentences, loan and insurance approvals, hiring practices. These are people have tried outsourcing these things to AIs because the AI should be fair. No, it wasn't at all. These were disasters. Data bias is a big part of the problem. You have to remember the AI there's a viewpoint that I teach in one of my graduate classes that AIs are just a compression of their training data. It's a model that basically takes the training data and shrinks it down to a single neural network. But it contains nothing that is actually not in the training data already. and it tries to contain everything that's in the training data, which means if, for instance, society tends to issue longer prison sentences to Black men, then the AI will learn that Black men should have longer prison sentences, because that's the data that is fed in, not that it's morally correct. The AI cannot make moral judgments about its training data. It just sits there and is fed training data and just sits there going, more data, please. That's all it does. And so the racial disparities do show up. And if they had been suggested by humans, somebody would have gotten fired. But the AI is just a machine. It has to be fair, right? No. Explanations are expected to be a major approach to countering bias, because the AI won't lie about it. It won't try and hide what it's doing. If the training data leads it to form a rule that Black Americans should receive smaller loans than white ones, it will spit that out as a confident, approved rule. Yes, this is what my training data says. I'm proud to say that. Except it's not really proud. It's just saying it loudly and clearly. It will flat out tell us what the biases are. Now, with all this being said, we can start talking about what is an explanation anyway. So, let's start with philosophy. And what do exactly we mean by opaque or transparent? So in 2019, Zednik argued that an AI has a number of what he called epistemically relevant elements. That's a fancy philosophy term for how do we know what we know. So these are things that could be cited in an explanation and can help define what the AI is doing. This includes input values, their distributions, details of the AI algorithm, how it was trained, the internal calculations for a given input, the outputs for a given input, etc. The importance of all these different things likely changes for different groups of users. So AI developers are going to be much more interested in the detailed internal calculations because they're looking for bugs. A regulator or a lawyer is much more interested in the input-output mapping. Ordinary users want to know if this thing is actually going to do a HAL 9000 on us, and we should not trust it to drive our cars. Opacity, being opaque, therefore means the user who's trying to understand things lacks knowledge of important epistemically relevant elements of the AI. The less the observer knows, the more opaque the algorithm is. The more they know, the more transparent the algorithm is. So explanation then is a means of reducing opacity by communicating those epistemically relevant elements to the observer, the user. So that's the goal. Now, how do you actually carry it out? A lot of different areas in the social sciences have studied this. So Miller in 2018 had a major paper on explainable AI and how social science viewpoints on explanation could be applied to it. So this is the framework he used. We have two social actors. We have an explainer who knows something and an explainee who needs to know about that something. So the explainer is the one going to be communicating an explanation to the explainee. What are they going to explain? Well, something, whatever it is. This is the explanandum, the thing that is being explained. The explanation itself, which is trying to communicate those epistemically relevant elements, is the explanans. This is the thing that we are trying to create in XAI, an explanans about an AI, which is the explanandum. The explainer has more knowledge of the explanandum. So this would be essentially a deep neural network and an interface, call it an explanation interface, built for the AI to generate and communicate an explanans to users of the AI. You'll notice that this arrow is two-way. The explainee can communicate in a variety of ways to the explainer that they need more. They don't understand something. This is why explanation is considered a social act. It is a discussion between, an interaction between the explainer and the explainee, not just a straight dump from the explainer to the explainee. Now, in a room full of academics, this probably seems pretty obvious. We call it active learning, and it's considered a best practice for teaching. But how do we set this up and actually execute it when the explainer is the AI and the explanandum is the AI itself? So when I said explanation interface, I was serious. This needs to be a major part of your system functionality designed in from the beginning. This was done back in the expert system days, Mycin and its relatives, back in the early to mid 1980s. But you don't see it so much anymore in modern AIs, partly because it's a much harder problem to generate an explanation out of a deep neural network versus a rule-based expert system. But it does still need to be there. So I'm going to use the term explanation interface, or EI, as a generic general term for the functionality of an AI to explain itself to a user by producing and communicating an explanans. Right, so we have the system component. What are the design goals? Because this is engineering, you have to have design goals. Well, there's a lot of discussion about that. It's not as simple as 2 + 2 must equal 4. You have to be able to communicate to a user, and users being human, what are the exact designs that communicate an arbitrary thing effectively to a human? Nobody really knows. There have been some suggestions. So Swarthout and Moore in 1993 proposed these 5. Fidelity, the explanans has to actually reflect the processes used to reach a decision. Understandability, well, yeah, the explanans must be comprehensible to the users. Sufficiency, the explanans has to provide enough detail to justify and defend the system's decisions, possibly even in a court of law. In fact, these days, quite likely in a court of law. Number 4, low effort. Well, the development effort expended on the EI should be proportional to the total effort spent building the whole AI system. I mean, if you spent 99% of your time building an EI, the explanation interface, and only 1% of the time actually building the thing that actually does something, which is the AI itself, well, you haven't really used your resources very effectively, have you? Number 5, same sort of thing. Efficiency refers to the execution time. It should not be the total execution time of the AI should not be materially affected by adding an explanation interface. It sounds good, but the problem is some of these things conflict with each other at a very fundamental level. So the BERT network used to be the most complex thing out of there, but the GPT family has just blown it right out of the water. But even BERT, 345 million parameters in a massive deep neural network. A fully sufficient high-fidelity exponens for this entire network will be monstrously large. It is a well-known fact that a monstrously large rule set is not understandable. Furthermore, the time complexity for rule extraction is going to be very significant. It's super linear in every algorithm I've ever seen. 345 million parameters would mean a lot of compute time. The GPTs, like ChatGPT, with 170 billion parameters, is much worse. We don't even know what GPT-4 and I guess the new one GPT-5 even are. We don't know how many parameters they even have. That I don't believe that has been released as a white paper. But again, just more and more time. This is a more recent proposal from 2017, and we've gone up to 7 design goals now. Fairness, privacy, reliability, robustness, causality, usability, and trustworthiness. Interestingly, the development time and system performance objectives from 1993 are not included here, even though they really should be. I suppose part of the problem is 2017 is 6 years ago now. I don't even think BERT was a twinkle in anybody's eye at that time. So networks were, that's an era where the large deep neural networks were actually quite small by today's standards. Today, you would probably have to bring back system performance as a first-class objective.
Scott, apologies for interrupting. We still see your title slide. I'm not sure if that's intended.
What?
We still see the title slide.
Hang on. All right, let me get back. I don't know why. I've been scrolling ahead the whole time. I'm very sorry.
All right. It happens.
Okay, so why is this stupid thing not scrolling ahead? Sharing, share. Let me ask you this. Do you see the editing frame on my PowerPoint right now?
Yes. Yeah.
Okay.
We now see slide 13.
Okay, let me do this. Has it now changed to the title slide?
No, I think it's the presenter view problem.
Oh boy, I am so sorry, guys. Here I am thinking that things were scrolling ahead nicely. All right. And I had some nice video. I had some nice slides here too. Okay. So the slides will be posted, but what would you like me to do, Tim?
I'll post the slides so students can see them as well. And yeah, I think it's best to just go from the current point. If you want to hit highlights quickly to show the visualizations, I would say that's okay too.
All right, so we'll scroll back. Slide 8 was where we talked about the opaque versus transparent AI philosophy. So basically, the idea that this AI thing has multiple pieces, but you, the observer, cannot really see very much. Probably the most important slide was where I discussed explainer, explainee, and what an explanation is. So here's your explainer. That'll be the AI explanation interface. The explanandum is the thing you are explaining. That's the AI itself. Explainee is the user who needs to know about the AI. And the explanans is what is communicated from the explainer to the explainee. It is the explanation of this thing. And this arrow is two-way because the explainee needs to be able to request clarification or further information from the explainer. This is why it's considered a social act. Okay, well, let's pick up where we were. So the history of AI can be seen as a back and forth between symbolic and non-symbolic AI. Now, what do I mean by that? Well, this figure comes from information in Niels Nielsen's book, The Quest for AI. Symbolic AI is basically things that deal with AI as language. It's also called good old-fashioned AI. It's systems constructed around some form of explicit knowledge that is heavily leveraged in building the AI. And this knowledge is in a very comprehensible form for humans. Theorem provers and expert systems are good examples. Fuzzy sets of logic are also in this group. These algorithms are relatively easy to interpret and explain. Like I said, Myson in 1975 had an explicit explanation interface designed in. And Neomycin and Explain in the early 1980s were called second generation expert systems. And their motivation was to try and improve the explanations being offered. Non-symbolic operations, on the other hand, are computer algorithms that excel at some task we believe requires intelligence, but which bear little or no relationship to what we humans believe constitute human intelligence. So statistical machine learning. Neural networks. Game-playing algorithm like the automated checkers program or any of the chess programs that have been built over the years. They do tend to be more difficult to interpret or be opaque. The biggest ones, BERT, ChatGPT, are giant black boxes. They're used because they are so much better at natural language processing than anything else that is an alternative. One of the themes that you get out of this diagram is that there's a bouncing between symbolic and non-symbolic approaches, as one approach or the other gains or loses favor. Neural networks, particularly, are considered to have had two winters in which academic and funding interest in the topic dropped very sharply. The first one over here from 1968 until about 1982, that was caused by Minsky and Papert saying, poo-pooing multilayer perceptrons. There was a second one right about 1995 to about 2005, which came along as people were realizing that neural networks had a vanishing gradient problem, and the alternative of support vector machines gained traction. Then in 2006, Hinton published his paper on deep belief networks, and then convolutional neural network got ported to GPUs in 2011, and that really got people very interested academically in deep neural networks. And then in 2015, AlphaGo beat a top human player at the game of Go, and that was kind of the moment where deep learning exploded into the public consciousness, and people began to treat it as the new AI. DARPA's XAI program that a lot of your professors were funded by ran from 2016 to 2021. We also tended to find something called the accuracy interpretability trade-off. It's been observed for some time that the most accurate algorithms for AI are also the hardest ones to explain. So there seems to be a trade-off between things being more explainable and performing better. Are you seeing me click ahead to the next slide now?
Yes.
Okay, fine. Then we'll just roll with this. My notes pages on the slides include all the topics I was talking about here. So what Tim will be posting will actually have those notes in it as well. So where does fuzzy logic fit into all this? For the remainder of this talk, I'll look at 4 areas: fuzzy inferential systems, fuzzy expert systems, neurofuzzy systems, and then deep neurofuzzy systems. And I'll also talk about how explanation interfaces were or were not implemented for them. So this should be a familiar diagram to everybody now. Fuzzy inferential system is a rule-based inference system commonly used as an intelligent controller. So, for example, this is the Mamdani FIS, whose core is a set of fuzzy if-then rules. In other words, rules whose antecedent and consequent clauses are represented by fuzzy sets. Inputs from the real world come through a fuzzification interface, turns them into a fuzzy set, which the inference engine then combines with the rule base in a generalized modus ponens inferential process. This produces a fuzzy set output, which is defuzzified to produce a crisp system output, suitable for presentation to a control system, for instance. The key construct that makes this all understandable is the linguistic variable. So it's exactly what it sounds like. It's a variable that defined over a given universe of discourse, whose values are words, terms in natural language. Technically, a linguistic variable is a 5-tuple. X is the name of a linguistic variable. U is its universe of discourse. In other words, the universal set that each fuzzy set is a fuzzy subset of. We have a set of terms for the linguistic variable. These are words in natural language, directly assigned to a fuzzy set by the semantic rule that associates a fuzzy set of U with each term in T. It could also be that we need to generate additional terms, like if you have modifiers like very or moderately or some other modifier. These are generated through a syntactical rule, usually a context-free grammar, and then the semantic rule M has to have a way of associating each of those modifiers with a function that's applied to the fuzzy sets to modify them. So at the bottom here, we have our canonical form of a fuzzy rule. If X is small and Y is big, then Z is large. X, Y, and Z are variables belonging to their own universes of discourse. So we have two input dimensions, X and Y. Small is a fuzzy subset of the dimension X belongs to. Big is a fuzzy subset of the Y dimension. And then large is a fuzzy subset of the output dimension. We normally stop here and say, this is a linguistic rule, therefore it is interpretable. That is not really correct. There's no social act of explaining here, no means for a user to make queries. So this is not in itself an explanation interface. It's an AI whose form of knowledge is more interpretable than a neural network, for instance, but it's not a proper explanation yet. The FIS is also not an expert system. Now, both do use rules, but an expert system also takes into account the previous inferences that have been made, not just its current inputs. So on the left here, we have the working memory of an expert system. You have input data, obviously. You have conclusions from rules that have been fired before. These are considered facts, both of them. And then you have the antecedents of some unfired rules. This is called the conflict set. So we are attempting to match a group of facts to a group of antecedents. This is called the many pattern, many object matching problem. And a brute force approach to solving that problem actually has an exponential time complexity. Practical expert systems had to get around this. So back in the 1980s, they developed an algorithm called the REIT network, which arranges the conflict set of the tree and solves the many pattern, many object problem in polynomial time. Now, classic expert systems like Mycin had to deal with uncertainty because you had some uncertainty in your input data. Is this exactly 3.6 pounds of, I don't know, 3.6 pounds of ammonium nitrate? Or is it 3.7 pounds? In order to deal with that uncertainty, what Mycin did was threw around an ad hoc certainty factor for each rule. but it wasn't based on any proper mathematical foundation. So the certainty factors worked as long as you didn't add any rules. But when you did, you had to painstakingly rebalance the entire set of certainty factors. Otherwise, your computations went absolutely haywire. So in 1983, Zada suggested that his fuzzy sets and fuzzy logic would be applicable here. Linguistic rules would more naturally represent expert knowledge, and certainty factors computed using possibility measures and the compositional rule of inference would actually be robust and self-consistent, rather than you having to rebalance them all the time. So some expert system shells were built using these ideas. Fuzzy clips, fuzzy shell, both actually do employ proper rig networks. They were both built in the 1990s. But again, almost no attention was paid to explanation interfaces. When I went back and looked, I only actually found one fuzzy expert system that had an integrated explanation interface. Leung et al. 1989. Doesn't appear to have gotten a lot of traction. Fuzzy clips and fuzzy shell were really the ones that actually had a user base. Neural fuzzy systems. This is more common these days. So neural fuzzy systems started a few years before the second neural network winter hit. Late 1980s, early 1990s. I've always seen them as drawing inspiration from the knowledge extraction approaches to creating explanations out of a neural network. So basically, they try to apply fuzzy logic in a neural architecture to make it more explainable. So there's really two distinct approaches. Fuzzy neural networks have come to mean basically direct substitution of fuzzy quantities or operations into a neural network. Not changing the architecture, just changing what it computes with. A major goal being to make knowledge extraction from that same architecture a little easier. The resulting architectures are a bit more transparent, still not great. It's still a very large distributed pattern of weights in a neural network, which is not understandable to humans. But it's a little more transparent and tends not to lose too much accuracy. Neurofuzzy systems, in the narrow sense, can be considered specialized neural architectures that try to mimic a fuzzy inferential system. So what we have here is ANFIS by J.S.R. Jang in 1993, and it's probably the best known of these. Its design mimics a TSK fuzzy system to the point that you can read out the implicit rule base quite easily. But the parameters of the fuzzy sets in the first layer here are adaptive. So it is possible that they may adapt to something that looks very different than the linguistic terms they supposedly represent. Furthermore, this is somewhat limited. So a TSK fuzzy system, and therefore ANFIS, is known to be a universal approximator. But that is an existence proof, not really a constructive one. TSK outputs generally are linear functions of the input. So you can approximate any given curve using small line segments, but you have to make them very small. And since every line segment needs to be a rule, you need a very large number of rules. So, as a practical matter, AMPHIS networks of any reasonable size will tend to be less accurate than a fuzzy neural network or a crisp one because it is more limited in its representations. And once again, AMPHIS does not have an explanation interface. You can just do a post hoc rule extraction from AMPHIS. It's nothing that's queryable. So, deep neural fuzzy systems. Well, modern XAI focuses on explaining deep neural networks. So, LIME, SHAP, layer-wise relevance propagation, or LRP. These are all mostly post hoc explanations, coming back after a decision has been made and trying to account for why it was made that way. Deep neural fuzzy systems try to modify deep neural networks to be more transparent. And again, we see the same split as in shallow neural networks. Fuzzy deep neural networks versus deep neural fuzzy systems. So I'll talk a little bit about an example of each one. So a fuzzy neural network, a fuzzy deep neural network, can be constructed from restricted Boltzmann machines. That's a two-layer network, one externally visible, the other one being hidden. The layers are densely connected together, and the connection weights are trained via statistical algorithms. In 2015, Chen replaced numeric connection weights with fuzzy numbers. It's a pretty classical approach from fuzzy neural networks. He designed and tested a learning algorithm for that. And then Feng et al. In 2020 took this and stacked it into a fuzzy deep belief network. And that 2020 paper found that the fuzzy deep belief network outperformed the classical deep belief network and was more robust to noise. Alternatively, we could try designing a neural fuzzy system. So this is some work that my student Matava did in his MSc thesis. So we have a convolutional neural network, and the literature really views it as two pieces. You have your stacked convolutional and pooling layers. This is the automated feature selection component that everybody talks about. Following that, you actually have a classifier layer, one or more densely connected layers plus a softmax, which essentially is giving you a multi-layer perceptron as your classifier component. What we did was we trained these convolutional neural networks. Then we ripped the dense layers off, just got rid of the classifier component, and substituted a fuzzy classifier. What we did was use fuzzy clustering followed by the nearest prototype's algorithm to produce 10 fuzzy clusters and assign new data points to a cluster. We hardened the clusters to find a final classification. And we were fairly close to the state of the art on the MNIST data set. Our explanation interface approach was actually taking the midoid of each cluster as the explanation for the whole cluster. So the explanans we produced was to spit out the midoid of the cluster. And we compare that to individual predictions by backpropagating the midoid and each individual prediction all the way to the input layer. where we can then form a saliency map showing how important each pixel is to the two images. This is essentially layer-wise relevance propagation. More recently, instead of this fuzzy classifier, we are using a modified ANFIS as our classifier component. And that is turning out to be as accurate as the original convolutional neural network. So what does the future look like? Should we be focusing on explanation interfaces in fuzzy logic? I think so. A number of authors have pointed out that good explanations, effective ones among humans, are often based on counterfactuals. In other words, talking about something that didn't happen and explaining why did it not happen. It seems reasonable that creating counterfactuals from deep neural networks is difficult because weights don't really map to events. But a deep neural fuzzy system, which is rule-based, the rules do map to events. Therefore, it might be easier to extract counterfactuals from those deep neural fuzzy systems. I've also noticed that the XAI field is really insisting on quantifying explainability, not by some automated metrics that you can extract, but by actually validating a proposed interface in human trials. In other words, you've got to set up something like a classical information systems experiment where humans are asked to do a task and AI gets involved somehow, and then you ask the humans on a questionnaire, how did they react to the AI? And you also observe their behaviors on the task. This is fairly classic stuff in the information systems area, but not very common in fuzzy logic. Okay, so that's what I've got for today, and I'm ready to take any questions.
Thank you, Scott, for the talk. I'll defer to Samuel or anybody else if they have questions, but I have a couple of my own. Well, while other people may be putting their questions together, I'll go ahead and start with one. What is your perspective on confirmation bias in terms of humans only accepting the quote-unquote correctness or viability of an AI if it gives them explanations that they agree with?
Oh, let's start with something hard, shall we? Oh boy. That is an unfortunate tendency of humans that we may have a big problem with. The AI does not understand confirmation bias. And the scientists and engineers who build them really don't get involved with confirmation bias either. In this sense, we view the AI as a mathematical function. It isn't making a value judgment, and we don't assume that it's making a value judgment. Now, is that true for our users? There is some evidence that the answer is no. Some of the research that looks at explainability has found that humans tend to, I don't know if anthropomorphize would be the right word, but they tend to treat it as a intelligent, conscious agent. And that's extremely wrong because there's nobody back there. And it leads us to the big problem of confirmation bias, because confirmation bias at its base is really about, do you belong to my tribe or not? Are you sharing my values? Are you sharing my outlook on the world? The AI is going to disappoint you if you're looking for that. Because no, it does not share your outlook on the world. No, it is not a member of your tribe. You may, from time to time, see responses that seem acceptable to you. You might see a bunch of them in a row. And therefore, you accept this thing behind the screen as a person who's part of your tribe. And then it goes and does something that's so wildly wrong, it has to be a bunch of horrible Democrats instead of good, honest Republicans. Right? Or substitute in whatever political divisions you have or other divisions you have in your society. And why does it do that? Because it does not know and does not care about your values. There is nothing to care in it. Caring is something that it cannot do. So, is there confirmation bias? Can it deal with confirmation bias? Not really. That's my thought, anyway.
Yeah. I would tend to agree in that sense. To expand out a little bit further, it seems to me that the utility of an explanation is completely dependent on the human's ability to accept it. You know, we're talking about trust in AI, and to extrapolate out a little bit, if we get to the point where we have, you know, for sake of argument, an AGI, or let's just say a system that has learned exponentially and from all the measures we have is more intelligent than any human or all humans, is an explanation about its behavior or decision making valuable at that point? We may not even be able to understand the explanation at that point.
Oh, yeah, the question of bootstrapping. Well, at the moment, that's a nice trope in science fiction, but I'm not aware of any evidence that anybody's ever produced that bootstrapping to superhuman intelligence is mathematically possible. A big part of the problem being we can't actually measure what is human intelligence and just what exactly does that mean. As I say to my AI class, which is the one I'm actually going to be teaching in less than an hour, consciousness, which is the phenomenon underlying intelligence, we don't know what that is. Nobody has any serious scientific idea of what consciousness might be caused by, or what its characteristics are, or what even the nature of the phenomenon is. I'm sitting here and I experience the fact that I am looking at a screen and I see an image of a person I actually know. But the inner life of Scott Dick is confined to my skull. You can't see that happening in my over there on the other end of the screen, and I can't see what's happening inside your skull. I know I am a thinking being. You might be a piece of cheese I have failed to digest, and I'm currently having a hallucination over. That's a very famous point made by René Descartes, the philosopher from France. Fundamentally, until you can actually tell me what consciousness is, and therefore what human intelligence is. The idea that a AI may duplicate or exceed our intelligence, frankly, doesn't make sense, because we cannot engineer something we have no idea what it is. And if we are going to build an AI, a true intelligent AI, we're going to have to engineer it. It's not going to appear by itself. So we're now treading on the very big question that AI was originally conceived to answer. What is intelligence? AI has made zero progress in answering that question. We know what it is not. It is all the fancy pattern recognition algorithms that we've come up with AI over the last, what is it now, 70 or 80 years. But none of those have created a conscious intelligence. Something else is going on. Tell me what something else is, and then we can discuss bootstrapping an AI to be something greater than human.
Well, I completely agree on the topic of consciousness. There are some very fundamental questions that need to be answered first. Thank you. Well, I'll turn it over to someone else to ask questions instead of hogging the mic.
Any questions from anybody else watching? Tim, I just called up the list of participants, and it's down to you and me.
Ah, okay. Well, well, I'll spare everybody a one-on-one conversation with Scott and I discussing consciousness and utility of explanations at the moment. If anybody does have questions, though, please put them in the Slack, and we can aggregate those and forward them to Dr. Dick as needed. Also, the Slack, I have to plug it every single time. Please join if you haven't already and you're in the competition or planning to compete, because there's a lot of discussion in there that's useful, not just from a philosophical and other point of view from AI more generally, but also implementation wise as you start developing your agents for the competition. So with that, we'll go ahead and close out today's talk. Thanks again, Dr. Dick, for joining us and giving your thoughts on explainable AI and where we might be headed and what we might need to do to get there.
Okay. Thanks, everybody, for having me. Have a good day.
Thanks, Scott. Bye.
Bye-bye.